Hey everybody. So we're going to continue talking about complex numbers, and as you can see, we're going to take a look at multiplication again. We did it early on, but we've added a few things, right? So we started with our definition of complex numbers, right? These z equals x plus iy, where x and y are real numbers, and we call x the real part and y the imaginary part because it's got this coefficient I, right, where I is just the number where I squared equals -1, right? So that was our basic starting point. And we gave these complex numbers a geometry, similar to how we give the real numbers a geometry by imagining the real line. We place them on this line. The complex numbers, because the real part and the imaginary part play very distinct roles, we put them on separate axes. And so we have this horizontal axis and this vertical axis. The horizontal is where the real part goes. The vertical is where the imaginary part goes. And it gives us a place to picture these complex numbers. They live in what we call the complex plane. Well, with that in mind, we're able to write them in the polar form, right? Which is exactly how we translated polar coordinates before. We turn the x part, let's write this here, we can put these in the complex plane as x, y coordinates. And then we can rewrite x and y using the same construction we use for polar coordinates to write our complex numbers in these polar forms. Z equals r cosine theta plus I sine theta. And the connection is the same as it is in polar, right? We have theta is the inverse tangent of the y coordinate over the x coordinate, where we have to add pi if it's in the second or third quadrant, and so on and so forth, right? So we've seen that before. Right now, it doesn't feel like very much interesting is happening geometrically because we're just doing what we do with coordinates and polar coordinates that we've done previously. But we'll see when we revisit multiplication, we start to get some more interesting kinds of ideas. And I had also introduced this exponential form, which is a little bit, might seem a little bit unbelievable, but it turns out to be a good representation of these numbers. These all represent the same point in space, right? These are equal. X plus iy is equal to r cosine theta plus I sine theta is equal to r e to the I theta. Okay, so let's jump into multiplication. We'll start with just a quick review. So if I have two complex numbers, a plus bi, and w equals c plus di, then if I multiply them together, sorry, I've got a little something in my throat this morning, a plus bi, c plus di, we can expand as we always do. This looks like ac plus adi plus bci plus bdi squared, right? So I'm just foiling this as you would. And we can reorganize this, that I squared becomes a -1, and we get AC minus BD plus AD plus BCI, right? There's our new complex number formed by multiplying these two complex numbers together. Let's look at this same thing in polar coordinates, right? So if we were given these numbers, A plus B, C plus D, A plus BI and C plus DI, these two complex numbers, we could convert them to polar form, and we would write Z as R1 times cosine theta 1 plus I sine theta 1. And W would have some other radius or modulus, and we'd have a different angle that I'll call theta 2, right? So let's multiply these two together. So we'll take Z times W. So we'll have R1 cosine theta 1 plus I sine theta 1 times R2 cosine theta 2 plus I sine theta 2. Do a little rearranging, right? Everything's being multiplied here. We have 4 factors, the 2 radii, and then these 2 trig parentheticals. So I can bring the radii together, R1, R2, and move these to the back. Cosine theta 2 plus I sine theta 2. And now I'm just going to expand those two terms at the end, R1, R2. This is, remember, R is just a regular real number. There's no complex part to this. It's just the number, the x squared plus y squared, the square root of that. So we're just multiplying two numbers together here. Let's see what happens when we expand. So I'll get cosine theta 1 times cosine of theta 2. And then I'll get cosine theta 1 times I sine theta 2. So I'll just write the I out front and we'll have cosine theta 1 sine theta 2. Then multiplying I sine theta 1 times cosine theta 2, I'm going to get I times sine of theta 1 cosine theta 2. And then the last two terms, the last term from each of these, we're going to get an I squared and then a sine theta 1, sine theta 2. Let's do a little rearranging again, R1, R2. So that I squared becomes negative 1. So this becomes minus sine theta 1, sine theta 2. And I'm going to move that to the front with this cosine theta 2 minus sine theta 1, sine theta 2. And then I can factor an I out of these middle two terms. So we have cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. So here's where something really magical and interesting happens. If you look closely, this here, this is exactly, if you look at the sum formula for cosine, this is exactly cosine of theta 1 plus theta 2. All right, so go back and look at your sum formula for cosine, and this is exactly what you get. So we're just going in the opposite direction. And if you look in this direction, or look at this part, the part underlined in blue is the sum formula for sine of theta 1 plus theta 2. Right. So when we multiply, this is I think quite astounding, right? That with this little notion that this I squared equals -1 and writing this way, we wind up, when we multiply these polar forms together, something very, very interesting. What happens is that you get the product of the moduli, the product of the two radii, and then you simply add the angles together, right? This is a new complex number whose new radius is just the product of the two radii of the numbers that were multiplied together, and the angle is simply the sum of the angles of these two numbers, right? Notice this also corresponds exactly with what would happen if we used the exponential form, right? So if z would be r1 e to the I theta 1, w would be r2 e I to the theta 2. Well, we just use the rules of multiplication. We can move things around and move those radius numbers to the front. And we get e to the I theta 1, e to the I theta 2. But when you multiply two things together that have the same base, you can add the exponents together. So we'll get e to the I theta 1 plus I theta 2. And then in that exponent, we can factor out the I. And so again, in this form, we see that if I'm telling you to believe me that we can write complex numbers this way, that's really only useful if it follows all the rules of exponentials, right? Because we're using this notation, and it does. And it turns out that we can use all the rules we have for exponents when we have our exponential form. And again, we see multiplying them together here is simply the product of the two real numbers that are the modulus of the two complex numbers. the radii, r1 times r2, and you just add the angles together. This seems astounding to me, right? It still blows my mind that there is this really neat consequence of what seems, it's very difficult in the beginning to see why in the world does this even come up when we're talking about trigonometry, this complex numbers with this I squared equals -1, and somehow there is something, this feels like there's some deep connection, right? Because we get this very simple way to multiply. And we'll see more about what this means geometrically in just a minute. Let's do an example. Let's take some numbers, two complex numbers, and go through a few of the things we just did. Whoops. Okay, so let's take z to be 3 root 3 over 2 plus 3/2 I. And we'll take w to be -1 plus root 3 I. Okay, so there's two complex numbers written in their rectangular form. So let's do a few things. Let's first, let's multiply these two numbers in the original way we learned. So z times w is going to be 3 root 3 over 2 plus 3/2 I, -1 plus root 3 I. So remember what happens, we get the product of the two real parts. So let's just go back and review this formula we came up with. What do we end up with? We get the product of the real parts, A and C, minus the product of the complex parts. So I don't need to go through all that work of foiling and combining. So I'm going to get -3 root 3 over 2, and then we'll get minus 3/2 times root 3. So -3 root 3 over 2 plus I times, and we get the sum of the products of the cross terms. So we're going to have 3 root 3 over 2 times root 3 plus 3/2 times -1, right? So that's just this portion, okay? So let's make sure I did that right. Right. So let's see what happens. Well, we have two halves of the same thing. So this is -3 root 3 plus I times, let's see what we get here. So I'll just do a little scratch work. 3 root 3 over 2 times root 3 is going to be 3 times 3 over 2 plus 3/2. So this will be, or sorry, minus 3/2. There's that -1 there. Minus 3/2. So we've got 9/2 minus 3/2 is 6/2 or 3. So we get 3. So our number is ending up as -3 root 3 plus 3i. Let's just rewrite this way. -3 root 3 plus 3i. So there's the product in rectangular form. Okay. All right, now let's convert both of these numbers to polar form and then try multiplying them and see what we end up with and see that these correspond. All right, so let's go ahead. So let's convert z. For z, let's convert z to polar. All right, first we'll need, let's find r is going to be the square root of the real parts squared. So 3 root 3 over 2 squared is going to be 9 times 3 over 4 plus 9 over 4. Yeah, we got 9, 3 over 4. Okay. And then this will be, so we're getting 27 over 4 plus 9 over 4 is 36 over 4, which is 9, square root of 9, and we end up with 3. And theta is going to be the tangent inverse of 3/2 divided by 3 root 3 over 2. This is in the first quadrant. X and Y are both positive, so we don't need to add pi. And what is this? This is going to be the tangent inverse of 1 over root 3. And so you can take a look at your unit circle. This will turn out to be pi over 6. Right? So that means we can write z as the radius times the cosine of pi over 6 plus I sine of pi over 6. Right? And it's simple enough. Evaluate cosine of pi over 6 and sine of pi over 6, multiply by 3, and you'll see you get exactly what we started out with, right? It's just another way to write these same numbers. And we can also write this in its exponential form. This way, 3e to the I pi over 6. All right, so there's z. We can do the same thing to convert w to polar. So r is going to be the square root. So where's my w? So we're getting -1 squared plus root 3 squared. So we're getting the square root of 1 plus 3, or 4. Square root is 2. Theta is going to be the tangent inverse of root 3 over -1. But this point, -1 root 3, is in quadrant 2. We need to add pi to this. So this ends up being, let's see, negative pi over 3 is the inverse tangent of this, plus pi gives us 2 pi over 3. Okay, and so now we have w equal to the radius times cosine of 2 pi over 3 plus I sine of 2 pi over 3, or 2e to the I 2 pi over 3. Let's fix that up. That looks pretty sloppy. Maybe I'll write this as 2e to the I times 2 pi. That's a little, I think, a little clearer to read. Okay, so there we have it for the conversions. Let's take these numbers now. Let's do it this way. Let's go ahead and convert. We're going to need some more space. So let's take what we have. Let me copy a few things. We need these 3 pieces. So we have ZW. When we did it in the rectangular form, looks like this. And we also have now our polar forms. I'll write them as this. It's easy enough to convert. And W is equal to 2e to the I 2 pi over 3. Okay, so let's go ahead and multiply z and w together using the new polar form. So let's do it, yeah, we'll do it as 3 cosine pi over 6 plus I sine pi over 6. And w is 2 cosine of 2 pi over 3 plus I sine of 2 pi over 3. When we multiply ZW, so the rule that we discovered was all I need to do is multiply these 2 radii together. So we'll get 3 times 2. And then I have cosine of pi over 6 plus 2 pi over 3, right? I'm simply adding together the 2 right, which we can simplify as 6 cosine. So pi over 6, 2/3 pi is 4 pi over 6. So we end up with 5 pi over 6 plus I sine of 5 pi over 6. Okay, so that gave us a much simpler way to multiply them if we already had them in polar form, which we often will. It's a very nice thing. let's just confirm that these are the same numbers. So it should be the case, right? There should be no difference between doing it this way and doing it this way. So let's convert, since we already practiced converting rectangular to polar, let's convert ZW, let's convert this polar form into rectangular. We know that X should be equal to R cosine of theta. So that's going to be 6 cosine of 5 pi over 6, which is 6 times the cosine of 5 pi over 6 is negative root 3 over 2. Multiply these together, we get negative 3 root 3. And the imaginary part should be r sine theta, which is 6 times sine of 5 pi over 6. And that is 6 times the sine of pi over 6. 5 pi over 6 is 1/2, and that is equal to 3. And these are indeed the coefficients, the real and imaginary part that we see up there. And so our rules are fitting together nicely, which of course they should. They should not contradict each other, okay? So let's just geometrically what we've seen, the product of two complex numbers in polar form gives us a new number, a new complex number with a radius that is the product of the two original radii, and whose angle is the sum of the original angles. So let's just look at a picture of what we just did. So here's a graph, and I've got, let's choose, how about bright pink? Shouldn't be confused when I do these. So here's Z, I'll label it a little bigger since that's pretty small. Here's W, and here's the product Z times W. So let's draw a few things in. I'm going to draw a line from the origin to Z. We know the angle for Z is pi over 6. Do the same thing to W. This angle was 2 pi over 3. And then this one's a little bit tougher to draw. Pretend that's straight. And this is simply a sum of these two angles. So it's one way we can interpret this is that the multiplication, 5 pi over 6 is what that angle was. The multiplication does two things. It scales. So if I think of, let's take Z to be kind of our original number, and we're multiplying it by W. What did W do to Z when it multiplied it? It scaled it by its modulus, right? So Z is now a number whose modulus, the product of ZW is a number whose modulus is the scaled modulus of Z scaled by the modulus of W. And it rotated it by the angle that is associated to W, right? We can see this even more clearly if we, let's put in a polar grid. This shows us the angles. You can see Z has pi over 6 as its angle. 2/3 pi is 4 pi over 6, 4 of these big sections, and we simply rotated Z by this angle of 2 pi over 3. We rotated it around as we scaled it to get to ZW. And so there's this kind of neat geometric interpretation. And if we think a little, boy, my straight line to ZW is not straight at all, but we can pretend. If you, for instance, multiply a complex number by a complex number whose modulus is one that's sitting on the unit circle, all you do is rotate it, right? All that ends up happening is you rotate it. And if you multiply it by a number whose angle is 0, that's going to be a number sitting on the positive x-axis, then all you're doing is scaling it, right? Which is already what we think about when we just, that only has a real part. Its imaginary part is 0. All we do is scale it. If our real part is 1 and our imaginary part is something, then all we're doing is rotating it. So we get some neat geometric consequences that turn out to make this very useful. Okay, that's it for now. We will do more on this in further videos. Thanks, everybody. I will see you next time.